This is your turn. Next speaker, move down to the California. California lady. Uh, she's my friend, a co-host of this program, Shirley Meng. She received her PhD degree in advanced materials for micro and nano systems from the Singapore MIT Alliance in 2005. Shirley currently holds the Jaebel Chair Professor at UC San Diego. She has so many director's positions. She's Director of Sustainable Power and Energy Center, SPEC, since 2005. I'm glad to point out that she has been working with LGES for many years via our academia collaboration program, EIC. Her recent research interests are varied, everything, but to the recent interests, I can say solid-state batteries and functional battery materials for next generation energy devices. Her presentation title is Understanding the Interfacial Phenomena in All Solid-State Batteries. Shirley, now it's your turn.
Thank you, Dr. Ban. This is a great event to be present, and we will share our data on the solid-state battery development. And we want to thank the support from LG Energy Solutions. I do think that the attractiveness of all solid-state batteries, Professor Linda Neza has given such a wonderful introduction that I don't have to go through the details of solid-state batteries. I do want to say that at academic institutions, prototype cells in the reasonable size single layer pouch size can be made. And you can see that one of the major attractiveness for solid state battery is its safety. And it goes beyond that because as Professor Linda also pointed out that when we thin down the solid electrolyte and make a very thick loading of the cathode, there is a potential pathway for us to achieve higher energy density at the pack level. And more excitingly, that the processing scientists have figured out ways, particularly led by scientists in solid power, that the existing lithium manufacturing facilities may be able to be deployed when we make all solid state batteries. So I think my talk today will really focusing on the science, because what really excites us, like Professor Whittingham said, that do something different. So we always ask ourselves, for solid state batteries, when we are utilizing the property of the solid state electrolyte, that the non-flow and the rigid properties is obviously a challenge, but it also could be an opportunity for us to think about the next generation batteries. So in this chemical review paper, we clearly pointed out that the non-flow properties of the solid-state electrolyte actually is a curse and a blessing, because for liquid, if you have alloying type of anode materials like silicon or lithium metal, the continuous penetration of the liquid can cause a problem with the cathode electrolyte interface or solid electrolyte interface on the anode side. So can we utilize the solid state electrolytes non-rigid, non-flow rigid properties? That's a question to ask. And also we want to avoid the cumulative disadvantages from both the liquid and solid system. So today I will be mostly focusing on understanding the interfacial challenge. And then later part of my talk, I will mention a little bit about the mechanical challenges in the solid state batteries. And I stress again, in the all solid state batteries we make, there is no drop of liquid in our cells. So before I dive into the details of the scientific discoveries, I think it's very important for all of us to step back and look at the history a little bit. So in fact, Dr. Michael Faraday is the founder of solid state ionics field. In 1831, the silver sulfides was discovered, and the room temperature conductivity of silver ions, in my opinion, is probably the beginning of the solid state ionics field. In 1967, Yao and Kummer's paper is a very well written. I encourage everybody to read it. It's actually reporting the sodium ion conductivity in beta alumina at room temperature. In fact, in my own research group, we started with all solid state sodium batteries before we won the contest in the BIC for the LG energy solution. And sodium solid state batteries is also a very promising field for the future batteries. In the 1990s, Oak Ridge National Lab has a team of scientists who discovered and synthesized the lipon. That is one of the first few electrolytes that showed total compatibility with metallic lithium anode. As everybody knows, that the lipon is actually at some stage was commercialized to enable lithium metal anode, and more than 10,000 cycles has been demonstrated in the lipon electrolyte. In 2011, Kato and Kano, the Japanese team, showed that LGPS can have superior conductivity that shows ionic conductivity is better than that of the liquid electrolytes. And in 2013, I was totally impressed by a paper out of University of Colorado Boulder, led by Professor Serhii Lee's team. Actually, the first author, Tom Yusek, later joined my team in UC San Diego and helped build the all-solid-state battery research. In their work, they enabled the first conversion cathode materials with iron sulfides paired with lithium metal anode. And I think that's really took off the research in the solid-state batteries in my research group. And very recently, I think many of us overlooked the Braga and the Goodenough's paper for the glassy electrolyte that was released in 2017. And I think in 2017, many commercial entities, companies like Panasonic, Toyota, responded to release their plan for solid-state batteries. So I hope that shows you that solid-state batteries have a very long and rich histories that we can learn a lot. And then, we are indeed standing on the shoulders of the giants, the pioneering scientists in this field. So when we look at the difference between the liquid and the solid, one of the obvious differences we all should understand is when we deal with intercalation chemistry, like graphite and LNMO or NMC or lithium cobalt oxide cathode, the electrolyte based on the carbonate electrolyte, they are chemically stable. That means the HOMO-LUMO is actually outside the stability window. The anode and the cathode, they are stable when you just assemble the battery. When you start to sweep the voltage, then the formation of the interfaces is very important. That's the working mechanism in the liquid electrolytes, and our pioneer scientists have studied a lot. I think today earlier talk by Professor Jeff Down shows there's still a lot of room to be improved when we change the interface stabilities of the graphite and the NMC cathode. In terms of the solid electrolyte, particularly when we choose sulfide-based electrolyte, one will ask, why would we choose sulfides? Because the stability window is so low, right? Sulfides also have another challenge, is that they are chemically incompatible with the NMC or LiCo cathode materials. So what happened is that the chemical reactions first needs to be stopped. And that's one of the reasons that the road for solid-state batteries are very, very difficult, because many people pick the oxides as the first solid electrolyte top priorities to study. But sulfides indeed took quite a long time, because not only we have to deal with electrochemical stability, because when you start to sweep the voltage, the stability will change. So this become a double jeopardy for our solid-state battery development. However, again, thanks to our industrial partner who, colleagues, I would say, Toyota, who released the coating of the lithium niobate oxide, that gives us some hope that barrier layers like lithium niobate oxide that can stop the chemical reactions at the solid state electrolyte interface could potentially enable the utilization of the sulfide electrolyte with the NMC-based cathode. And in the last few years, we are very glad to collaborate with this logo should be changed to Energy Solution, but pardon me for still using the old logo, that the NMC 811 cathode materials that using a single step borate-based coating, and this borate actually was pre-selected by my colleague, Professor Shirley Meng's screening process by computation that could have a very good protective nature for the NMC to the aldehyde electrolyte. And once we establish the right environment for the boron, lithium boron oxide coating, we can then stabilize the cathode materials very well. So you see the utilization here is still not perfect, and I will dive into the details why at that time we cannot utilize all the capacity on the NMC 811 cathode materials. So once we solve the chemical stability, the next thing we need to worry about is really the electrochemical stabilities. Because the sulfide electrolyte has a huge challenge because it has very narrow electrochemical window. So if, like Professor Linda Neza already shown, if you have put in a lot of carbon in your solid electrolyte, you make a pseudo batteries like this to basically make the aldehyde electrolyte as your cathode. You can observe this very nice redox peaks from the oxidation of the solid electrolytes. So while we are, before we do any optimization of the cathode materials, indeed, when we charge the voltage of the NMC to higher voltage, we run into the trouble of oxidizing the solid electrolyte. As we know, on the NMC-based cathode materials, carbon additives is typically needed in order to enable the cathode materials utilization. So we can't put a lot of carbons into the solid, onto the cathode electrodes because that will induce a lot of the side reaction. So these stability issues with the solid electrolyte against the NMC cathode has been really a big challenge. So what happened is that you can then investigate what happened. So we spend the time to think about electrochemical reaction happens. Let's try to understand what are the products of the electrochemical oxidation process. Are these products good or bad for interface transport, for ion transport, or for electron transport? So we carried out a very detailed characterization to understand the reaction mechanism of the aldehyde solid electrolyte, and both of these plateaus are carefully studied. So these are electrochemical signals just coming from the aldehyde electrolyte. And you can see the low voltage phosphor reductions is actually a one-step process. However, when you have this sulfur, the higher voltage plateau is actually a sulfur reduction and oxidation, and it's completely reversible. So understanding this is very, very important because just like the liquid-based electrolyte, we need to understand the interface in order to optimize the cell cutoff voltage, the cell constructions, etc. So the redox reaction pathways also have been confirmed by our NMR expert from the Lawrence Livermore National Lab, Dr. Thomas Marple. NMR is a very promising technique. So with this group of techniques, we were able to confirm that the redox reactions in the aldehyde electrolyte, on the negative electrode side, you will form Li2S, lithium chloride, lithium phosphate. On the positive electrode side, you will form P2S5 or sulfur components. And this is very critical for us to later think about how to engineer these cells so that we can, instead of fight against the redox reactions, we can utilize and think about how to stabilize the aldehyde electrolyte. So one of the most critical experiments we have done is to look at the impedance change on the anode versus cathode. So 3 electrodes experiment is also applicable in solid state battery. In fact, when we look at the impedance spectroscopy, you can clearly see the difference between the anode SEI versus the cathode SEI. So on the anode side, we are very lucky because the product is very good lithium ion conductors. We can get a reasonable conductivity curve at room temperature. We're not that lucky if the large amount of sulfur is being generated on the cathode side. So this is one of the obstacles we must overcome for the cathode constructions with the algidide-based electrolyte. And one of the effective ways to overcome the challenge is actually to minimize the carbon contact with the solid electrolyte. So as you can see from this set of experiment, if we replace the very high surface area, very conductive carbon black with the equally conductive but much low surface area vapor growth carbon fiber, we can actually minimize the decomposition of the cathode, and then we can cycle the cathode NMC811 with the algidide electrolyte. Of course, this NMC811 is protected with the borax coating. But the effective current density, I would say the critical current density still remains low, but we did solve this cathode interface problem. And in the more recent program we are doing, we have successfully managed to make cathode electrodes through dry electrode processing that obtain more than 10 milliamp hour per centimeter square loading. And we can actually, using these vapor growth carbon fiber and special binders to achieve very, very good utilization of the cathode materials. So this is recent data in one of our archived paper to showcase that high loadings are possible in the NMC cathode. Yes, the temperature here is 60 degrees Celsius, but please be reminded that we have more than 10 milliamp hour per centimeter square loading for the cathode. So now we have a more or less promised cathode electrolyte interface. The challenge for us is really, like Professor Neza pointed out, the holy grail is whether can we enable lithium metal anode, because to deliver the promised energy density, we need to enable lithium metal. So the previous belief of solid electrolyte as a physical barrier against the lithium dendrite are mostly being crushed, because it's quite clear that in solid state batteries, dendrite shorting can happen. The good news is when it happens, the cell just fails. There is no thermal runaway event. So let's look at some of the interesting properties of the lithium metal, because the earlier work done by Professor Sakamoto's group is really on the fundamental of the mechanical properties of the lithium metal. And that taught us that when we design the solid state batteries with lithium metal, going for very high stack pressure may not be the most effective method, because lithium has very low yield strength. It's less than 5 megapascal. So think about when we put very high stack pressure, what could be the result? Because in solid state batteries, we typically put tens of megapascal stack pressure. So my postdoc, Dr. Jean-Marie Doe, initiated a systematic studies with the pressure-controlled load cells to investigate the lithium symmetric cells. And it's very interesting observations whenever we go below 5 megapascal. I mean, we also have 2 megapascal or 1 megapascal data, but whenever you're below 5 megapascal, you can shuffle lithium in the symmetric cell very long term. But if you do it at a very high pressure, then the cell shorts, and it correlates so well with the amount of pressure. The higher the pressure you go, the quicker the cell will short. And to peek into the solid state batteries, it's very important that we have a tool that can allow us to look at a buried interface. So with the micro CT that we have, we were able to look at mechanically induced short circuits. And when the pressure gets lowered, the plating of the lithium metal can be eliminated. So that give us some very good directions to think about lithium metal anode. Perhaps the very high stack pressure is not needed. However, we still have another problem, which is the critical current density, right? So even though we lower the pressure, we still have facing the problem because the cycle numbers I showed is always very, very low critical current density. So let's spend some time to understand what happened for the critical current density. Did we really produce lithium metal, or did we produce something else? Right. So the CT only shows you the morphology, but doesn't tell you the chemical species. So in my group, we set up this kind of capillary cells where you can put 2 lithium anode on each side, and you have the solid electrolyte in the center. And with this very beautiful lab scale XRD, you can obtain very nice refinable X-ray data where you see the center is beautiful algidide electrolyte, and on both sides is the polycrystalline lithium metal. And when we start to cycle the cells, this technique can be used to peek into the buried interface and help understand what is being generated. So I would tell the audience here, we do not observe pure metallic lithium. What we see is lithium chloride, Li2S, and lithium phosphate. So this is a clear message to say that the dendrite formation in the solid electrolyte is still a wide open area for us to all to understand what happened, because whatever fresh lithium metal goes into the solid electrolyte, they do not persistently present as the metallic lithium. Instead, they became all these predicted species by my colleague, Professor Shirley Meng. They predicted the lithium sulfide, lithium chloride, and we can clearly see this in our capillary operando XRD patterns. So with that, we also want to say, we are running into a dilemma. We actually have to put the pressure quite low. And as soon as we, either you increase the critical current density or you put the stack pressure up because we want to have a very tight contact between the solid electrolyte and the cathode, we run into the trouble of shorting. So it seems like we do need a brand new anode strategy. So yeah, I want to show you that the stack pressure effect on the lithium metal cycling, we can cycle very well with the 5 megapascal for the NCA versus lithium metal at room temperature. Again, I stress the current density is low, but you do see the degradation, and these degradation, which I will mention later, but it's really complex effect due to the mechanical response of the solid state batteries to the stack pressure. If you look at the cathode effect, if you change lithium to lithium-indium alloy, right, the pressure has almost no effect on the performance of the cells. So this really, really propelled us to think about an alternative anode strategy. And we know indium is not a sustainable solution because the indium does have quite high price tag. So the lithium metal limitations has been very well summarized in this slide. When we run to the high critical current density, we can run into those void generation. And when we go to higher temperature, we can actually promote the side reactions between the cathode and the electrolyte. So what should we do with the anode strategy? So everybody knows silicon is a very promising anode materials. I think that in the liquid electrolyte system, most of the silicon will be utilized with graphite, and then you make some kind of silicon graphite composite. And it's very, very difficult to actually cycle the pure silicon anode. So again, the advantage of having graduate student is, my student Darren Tan just thought, well, while everybody is doing carbon silicon composite, let's think about, do we really need carbon in the silicon anode? Because the literature survey shows there's hundreds of literature papers every year for the silicon. However, nobody have explored using 100% silicon in the all solid state batteries and see what happens. So the hypothesis is very simple. I mentioned about the non-flow rigid mechanical property of the solid electrolyte. So when we have the liquid cells, the silicon will continuously break and the liquid will always flow into those cracks. And that's why the interface is very unstable for the silicon. But in the solid electrolyte, the first important thing is we want to explore if the silicon can form a stable layer with the aldehyde electrolyte. And if it can form, because there is no solid electrolyte inside the silicon anode, this interface that formed here will be largely two-dimensional. And then we can rely on the good diffusivity of lithium in the lithium silicon alloys to alloy the entire silicon anode. So this strategy also should work because we check the electronic conductivity of the silicon, pure silicon, not lithium silicon. Actually, the pure silicon, the electronic conductivity is magnitude order higher than the solid electrolyte. So it should work. And we also have previously shown the people in the field that there is the titration gas chromatography method. We can differentiate the trapped metallic lithium versus the SEI lithium. So we utilize this tool in our silicon research. And oftentimes we found the SEI after first cycle is actually stopped growing because the cell coulombic efficiency very quickly rise up to 99 and above. In some cases, it can reach 99.9. Right, so this method is very helpful for us to gain confidence. So the important aspect, what Darren, my student, was very courageous to try, is to think about, because of the narrow electrochemical window of the aldehyde electrolyte, so he completely eliminated the carbon. So as a controlled experiment, we want to show people if you do have carbon in the anode, what happens? If you do have carbon in the aldehyde electrolyte, as we know, the carbon will facilitate the side reaction. So this is where you have carbon. If you add carbon into the silicon, your voltage curve will look different. And what happens here is that these solid electrolyte I mentioned on the anode side, when the voltage goes to very negative, it will generate Li2S or lithium chloride. And in this particular case, we clearly detect the lithium sulfide here. So the XPS is also clearly shows the same observations because sometimes the decomposition product is not very well crystalline, and we can actually use the X-ray photoelectron spectroscopy to detect those decomposition species. So with that, I think in the cell performances, you can easily see that actually eliminating carbon give you better utilization of the silicon anode, and the interface can be stabilized very quickly after the first cycle. Of course, the work on the silicon is not done yet. There's still a lot of questions unanswered, but we are very excited to say that, for the solid state batteries operating at 55 degrees Celsius or for storage at 55 degrees Celsius for a long time, you can observe how stable the solid batteries is only because the interface is very, very passivating. And we are happy to see this type of stable voltage storage at a very high temperature. So, as the previous speakers also mentioned, the challenge for the lithium-ion batteries for the future is the temperature range. And for us, the most exciting thing observation is probably the coupled chemical mechanical phenomena in the silicon anode. So if we take the pristine micron silicon particles, of course, there's a lot of built-in particle morphology. You can see the large micron size silicon. And once we start lithiation, we found that yes, the dimension of the silicon does increase, but most of the dimension change is into filling the pores. And what most striking for us is when you start to delithiate, we form this type of very columnar large grains of the delithiated silicon, and the morphology of the first charge after first charge compared to the pristine are completely different, right? Because the lithiated silicon is actually very, very soft. So under the stack pressure of 20, 30 megapascal, the morphology, the microstructure of the silicon lithium completely changed. When you take lithium out of the silicon, it never goes back to the original shape. And this process is actually one step, and it's complete the change, complete the transformation. You can consider it as like a formation cycle for the solid state batteries. And we did quite a lot of after cycling characterizations, and we're happy to report this microstructure after the first delithiation persists upon further cycling. So yeah, in Darren's work, I think we utilizing this pure silicon, 99.9% silicon loading with very high area loading. And the utilization rate of the silicon is also very high. We were able to demonstrate a very high critical current density, wide temperature range, and high loading. And of course, this is small laboratory scale testing that we were able to demonstrate 500 cycles, but we think that this study opens up a new possibility that we can think about how to design solid state batteries. So I would like to spend the last maybe 5-6 minutes to talk about the importance of the stack pressure. As a material scientist, actually, my favorite things for controlling matter is, many of us controlling the matter through temperature or pressure. So we are actually very excited to see. So my early work on the liquefied gas electrolyte was really use pressure to liquefy gaseous species on the high pressure to become liquid. And we were very fascinated to see that pressure can be a very effective knob in controlling the microstructure and the morphology for the solid state batteries. Because the micron size silicon is mechanically, micron size silicon is actually mechanically very, very stable, right? So if you look at the pristine materials after 50 megapascal, you take a look at the interface of the solid electrolyte versus the silicon. Of course, this is not optimized, but the good news is that you really do not see huge microstructure changes for the micron silicon. And that behavior is completely different from the lithium metal case, because in the lithium metal, if you charge the battery at 50 megapascal, you induce the mechanical induced shorting very effectively. So there's still a lot of work to be done in the area of controlling the pressure. And I think for the scientists in this field, this is a very, very fascinating space. This is just a mini summary here. So we do some kind of thought experiment, right? If you just have low loading for the NMC cathode, 40 micron, and it's only 4 milliamp hour per centimeter square, and you shuffle 20 micron to the negative electrode side, so the negative electrode side will become 40 micron. But the solid state electrolyte, solid cathode is actually an intercalation material. So it will only have 4 or 5% volume change. So net, this cell will want to grow in its dimension. But it cannot grow because many of our cell, at least in the laboratory scale cell, it has a confined space. So that will generate pressure. So my new student, Grayson, who will be really focusing a lot on thinking about how to handle the pressure, particularly when we go multi-layer stack. So I think that this is a largely unresolved challenge, right? So if you look at here, we have 20 micrometer thickness change. But if you stack 10 layers together, that's 200 micrometer, right? For our battery researchers, we know it's very, very difficult to handle this. But I'm also cautiously optimistic there may be some very interesting stack pressure cell designs. As Professor Chong in the very beginning of today's forum mentioned about, this is an area that really wide open, not very heavily studied. It is very challenging, we understand, but for the future technology, we think there are many, many brilliant young people will come and resolve this challenge. So let's think a few things about the cell designs, right? Everyone seems to be already ruling out the possibility of the cylindrical cell format for the solid state battery. So I would challenge this notion because in the pouch cell, when we need to achieve very, very high pressure, the amount of force that's needed is very high because of the large areas. 18650 cells is actually a different story because of the smaller cell format. So think about where we can apply pressure in the electric vehicle. So we know there's a hydraulic pressure for the hydraulic suspension, and that's about the same magnitude of the pressure we need in the car. And there's also how we operate the argon tank. We use pneumatic pressure, also pretty high pressure. And in the prismatic cells, we know there's hard casing to leverage volume expansion. So we think that utilizing the nature of the silicon expansion, we could actually generate a stack pressure with the hard casing. Of course, this is a naive academic practice, and how we can really make that happen is still very challenging and under intense studies right now. And just for the fun of all the audience, I'm the only factor that's standing between you and your lunch in South Korea. I want to say that my students come out with this idea for submarine all solid state battery because the water obviously is one of the best way to exert the pressure. And this is my former postdoc, Dr. Avik Banerjee, who have contributed greatly to my group's solid state batteries. So this is just some crazy ideas for people to think about outside the box, to think about how we can enable pressure controls for the all solid state electrochemistry. So the remaining has a lot of challenges, okay? I mean, there's no doubt the cost is so high because the sulfur and lithium bond, L2S, one of the major elements, the lithium sulfur bonds are so expensive. So we have lots of issues to deal with. I summarize in this 3P: precursors, processability, and pressure. Because for solid state batteries based on sulfide electrolyte to work, we must think about the dry room compatibility and the processing ability. So I would encourage all of the audience to read this paper that really in the ACS Energy Letters very nicely, and together with a complementary summary coming from Japan group, you can see that and South Korea. So there's a lot of work that's ongoing for the solid state battery. And Professor Nazer said, our talk hopefully to differentiate what is the hype and versus what is the reality. I think the reality is that this type of configuration, perhaps not with lithium metal anode, but maybe with silicon, or possibly in the future that the new anode-free morphology can be designed. But the bottom line is that the 400 watt-hour per kilogram in the single cell format has been demonstrated. But we are still very far away, as I mentioned, that these 3 P, these three problems have to be resolved before we can move forward. And I also want to take this opportunity to thank the support from the industry. I think the challenges in the solid-state batteries is so dire that it's going to be very, very challenging, if not impossible, to be resolved by a single PI research model. So we do hope that among the academic institutions, industry, and the government funding agencies, that we can work together to bring the solid-state batteries to reality. So that concludes my talk, and I want to thank Professor Ong, Professor Chen, and the NMR expert I work with. I actually started my solid-state batteries through a basic energy science research for studying the LiPo lithium interface. And we are very, very fortunate to be able to continue the research under LG's support. And I also want to thank Shell for their support on the solid-state sodium battery research, which has generated a lot of useful insight in the lithium equivalent. Last but not least, I want to acknowledge my brilliant all solid-state band. Working with them is an absolute pleasure, and the young folks are really taking risks and doing things outside the box. So with that, thank you very much for your attention, and I conclude my talk.
And thank you for the amazing presentation, Shirley. I have actually one question. So you mentioned 3P, that is really challenging. All of my battery manufacturing companies, including LGES, day and night, 24 hours, 365 days, consider how we can reduce the cost. Currently, lithium-ion battery is the final boss in cost aspect. Do you think our solid battery could compete against the current final boss lithium-ion battery, and any possibility that can beat the lithium-ion battery in the future? Any idea? Really
yeah,
challenging
thank you very much.
Yeah.
Question. Yeah, it's a very hard question, but I do want to try to answer that. So everybody knows that lithium-ion batteries in the last 15 years, the cost reduction 10 times or more. And it really took the entire field to work on the cost reduction. So I think that the future for the solid-state batteries is challenging, but I would say that the lithium sulfur or sodium sulfur bonding. So first of all, the precursor, I do think that chemical companies like LG or some other chemical companies will come out with a scalable and very smart way to remove the first problem. So that I'm quite confident, because the sulfur is very, very abundant. So the precursor for the Li2S cost should come down. And the second problem for the for the processing ability. So there I see a huge opportunity for cost reduction, because we are mostly trying to develop a dry process. So that one, I think even the lithium ion cells are trying to go for that direction, because NMP solvents and a lot of the liquids actually cause issues during the fabrications. So I think, the most critical unknown is actually the pressure control. So I think that this one does represent a lot of uncertainties, and I'm hoping that young students will come to this research field. I think that to help decarbonize our society, lithium-ion batteries, like Professor Whittingham, Professor Dunn have mentioned, that will dominate in the next 5 to 10 years. I would more leaning towards 10 years, but solid state, we should have a clear answer in the next 5 years if the possibility for cost reduction is possible. At the moment, I see this pressure control is probably the most costly one, but we are, I have to say we are cautiously optimistic with all the students who are so young and brilliant and enthusiastic about battery research. Somebody might come out with a brilliant idea.
Yes. Thank you. Please educate good students for our future battery industry. Thank you so much, Shirley.